Can we solve the double pendulum using Newtonian mechanics?
Let's find out.
Okay, so here we have the double pendulum. It is a system that consists of two rods and two point-like bobs connected in a specific way you see on the screen. A rod of length L1 is connected to some fixed point in space, which we'll choose as an origin for a reference frame in which we're going to track the motion of the system. The x-axis of this frame is horizontal and the y-axis is vertical, as usual. At the other end of the first rod, we have a bob of mass m1 to which another rod of length L2 is connected. And at the other end of that rod is another bob of mass m2. So we have a simple pendulum connected to another simple pendulum in a way, which gives us a double pendulum. All of the usual restrictions and assumptions are present. We will restrict the motion of the system to a plane. We will ignore the dissipative effect of air resistance, naturally, and we will also consider the rods to be both rigid and massless. We want them to be rigid so they don't deform under the influence of any forces, so no wiggling, no stretching, and we want them to be massless so they don't contribute any inertia to the system. Now, since we are on a plane, a two-dimensional space, we need to assign two coordinates to each bob to uniquely determine the position of a double pendulum in any given time. We can then define position vectors for both the bobs, so let vector r1 be the position vector of the first bob, and let r2 be the position vector of the second bob. These position vectors have two components, one in the x direction and the other in the y direction. If we define x1 and y1 as coordinates of the first bob in any given time, and x2 and y2 as coordinates of the second bob in any given time, we can write down position vectors in terms of their components in the following way. So r1 is equal to x1 x hat plus y1 y hat, and r2 is equal to x2 x hat plus y2 y hat, where x hat and y hat are just unit vectors in the x and y directions, respectively. Even though we are in a two-dimensional space, both of these bobs actually have only 1 degree of freedom. That means we only need to calculate one coordinate of each of the bobs, and we can instantly know the other coordinate because the two coordinates are dependent on each other. The first bob is connected to a fixed point with a rigid rod of a given length. That means it can only move in a circular arc around the origin. So if we use the laws of motion to calculate the x-coordinate, we can immediately know the y-coordinate because in this case, the two coordinates are related through the equation of a circle of radius L1. Similar thing applies to the second bob. Once we have the position of a first bob, we only need to calculate the x-coordinate, for example, of a second bob through the laws of motion, because in that moment the second bob can only be L2 meters away from the first bob, so its coordinates are related through the equation of a circle as well. So 1 degree of freedom per bob gives us overall 2 degrees of freedom for the entire system. We can now tackle this by expressing y-coordinates as functions of the x-coordinates for both of the bobs, but we can make our lives substantially easier by introducing the angle that the first rod makes with the vertical, call it theta 1, and the angle that the other rod makes with the vertical, call it theta 2. This allows us to express all 4 of the Cartesian coordinates as functions of these two angles in a much more convenient way that doesn't involve square roots and denominators and exponentially more tedious maths, etc. So if we find a way to solve for these two angles, then we will solve the problem. To find the expressions for the Cartesian coordinates in terms of these two angles is a matter of basic trigonometry, and it is easy to see that x1 is equal to L1 sine theta 1 and y1 is equal to minus L1 cosine theta 1. The minus is there because the motion is going on beneath the x-axis, at least in the moment in time for which we created this picture. To find the expressions for x2 and y2, we only need to project the lengths of the rods on both the x and y axes, and then we will get x2 equals to L1 sine theta 1 plus L2 sine theta 2, and y2 equals to minus L1 cosine theta 1 minus L2 cosine theta 2. All of this is already familiar to anyone who tackled this problem with the Lagrangian method, but now it is time to introduce our boy Newton. Basically, we just need to write down Newton's second law for both these bobs. So just F equals ma, right? For the first bob, that is mass 1 times acceleration 1 equals the net force acting on the first bob, and for the second bob, the equation is mass 2 times acceleration 2 equaling the net force acting on the second bob. It is quite straightforward. We will now acknowledge the fact that acceleration is just the second derivative of the function position of some object with respect to time, so instead of writing a1 and a2, we will write r1 and r2 double dot. This dot notation is pretty commonly used and it makes the math a bit tidier. The number of dots just tells you how many times was the function differentiated with respect to time. Since we have already defined the position functions, the two position vectors, both of which are functions of time, we can just differentiate them twice to get the acceleration functions. We do that by differentiating their individual components. This is especially easy to do in Cartesian coordinates because there the unit vectors are constants. So we just get r1 double dot is equal to x1 double dot x hat plus y1 double dot y hat for the first bob, and r2 double dot equal to x2 double dot x hat plus y2 double dot y hat, because every single one of these coordinates is a function of time. The two Newton equations that we have are vector equations, and we can reduce them to four scalar equations, two for each of the bobs. So far, so good. Since we introduced the theta angles, we need to write down these acceleration terms as functions of theta 1 and theta 2. We already found the expressions for the coordinates, so we will just differentiate them twice with respect to time to get the accelerations. And we're going to do that on the next slide. Here on the left side of the screen, we have the expressions for the four coordinates. We will now take the first derivative, which will give us velocity functions, which were crucial for the Lagrangian method, but are kind of useless here. However, we need to find them first. Since the theta angles are also obviously functions of time, we need to be careful when differentiating these functions. x1 dot is going to be equal to L1 cosine theta 1 times theta 1 dot, and y1 dot is equal to L1 sine theta 1 times theta 1 dot. And by the same principle, we can easily derive the other two velocity functions. Now we will take derivatives of velocity functions with respect to time to get the accelerations. Since x1 consists of two multiplied functions of time, the cosine term and the theta 1 dot term, we need to do the chain rule again, which will produce two terms in the final expression. We get minus L1 sine theta 1 times theta 1 dot squared plus L1 cosine theta 1 times theta 1 double dot. We apply the same thing for y1 and then the same thing for the velocities of the second bob, whose acceleration expressions are going to have four different terms. And you can already tell that the math involved from now on is going to be so much fun. So we found the accelerations. Now let's turn our attention to forces. So while getting the equations of motion for this system is so much less time consuming with the Lagrangian approach, there's really nothing all that difficult to understand when it comes to the physics of this system. Let's do the free body diagram for both these bobs to show you what I mean. Okay, so this is the first bob connected to both of the rods. We can also add the theta angles into the picture because they will come in handy for finding the components of the forces involved. So what are the forces that act on the first bob? There's gravity, of course, that points straight down, let's denote it with Fg1, but there are also tensions in both these rods. Let's call the tension in the first rod T1, and that tension acts along the line of the rod, pointing away from the bob. Let the second tension be T2, which acts along the second rod, also away from the bob. And that's it. There are only these three forces: gravity and the tension forces in the rods, both of which are familiar to any high school student, maybe even a middle school student. That is what I meant by saying that there is nothing too hard to understand about the physics of the system. And while the expressions for these tensions are going to be absolutely horrendous, we can nevertheless see that they affect the system and easily determine in what direction they act. Let's write these forces down in terms of their components now. Fg1 is just minus m1g y hat. It points vertically downwards, so no components in the x direction. Again, just like with the position expressions, it is a matter of basic trigonometry to find the components of the tension forces. You can see from this diagram that T1 is equal to minus T1 sine theta 1 x hat plus T1 cosine theta 1 y hat, while T2 is equal to T2 sine theta 2 x hat minus T2 cosine theta 2 y hat. Fantastic. Now let's see what's going on with the second bob. There is gravity again, obviously, but since this bob is connected to only one rod, there is only one tension force that is directly affecting its motion, and that's T2 that acts along the second rod, and it is numerically equal to T2 that acts on the first bob because it is the same rod, therefore the same value for tension. And that's it again. There are no other forces on this entire system other than gravity forces and tensions in both of the rods. We can write down these two forces in terms of their components as well. Fg2 is just minus m2g y hat, and T2 is the precise opposite of what it was for the first bob. So minus T2 sine theta 2 x hat plus T2 cosine theta 2 y hat. Now that we know all that, we can return to our Newton's equations and plug in all these wonderful expressions for forces and accelerations involved. First, we're going to write them in a vector form. So m1r1 double dot is equal to fg1 plus t1 plus t2, as the vector sum of these forces is a net force. Also, m2r2 double dot is equal to fg2 plus t2. For scalar versions of this, we'll just plug in the components of these forces that we calculated a few moments earlier. Looks kind of threatening, don't you think? Well, kind of, but it doesn't look nearly as bad as it is going to look once we plug in the acceleration relations. Once we substitute those in, we get this absolute monstrosity, this awful system of four coupled differential equations. But this is actually not that difficult to solve. I mean, no knowledge of any advanced math is required. I mean, at least at this stage. The biggest issue here is that we actually don't know the expressions for T1 and T2, so we can't immediately turn to solving the equations. This issue is easily dealt with, however, since this is essentially a system of four equations with four unknowns, theta 1 and theta 2 double dot, the angular acceleration terms, and T1 and T2, the tension forces. Obviously, we don't treat thetas and theta dots as unknowns because we only need to solve for accelerations, and we get those as functions of time by integrating the acceleration functions, either analytically if possible or numerically, which is usually the case and definitely is going to be the case here. Even though the math involved here is pretty straightforward, I mean, we're basically just solving for some of the unknowns in this system of equations, this process is so incredibly tedious. Imagine doing the Lagrangian method for the quadruple pendulum. Yeah, you basically just take derivatives of polynomials and basic trig functions, but you're doing it for half an hour to get the final result. You definitely don't get the urge to punch someone. Anyway, let's bring this thing home. Notice that there is no T1 in the bottom two equations, which means we can easily express T2 in terms of everything other than T1, which is exactly what we need. We don't mind that the expression will contain theta 1 and theta 2 double dot, because once we substitute it in the third equation, we will have a new equation which doesn't involve tension forces at all, which is the goal we're trying to reach. Yes, the resulting equation will contain both theta double dots, but it doesn't matter. Both equations you get with the Lagrangian method also contain both theta dots, and then you treat them as two equations with two unknowns and solve for the two theta double dots. I'm not going to do that in this video, since the goal of it is just to get the same equations as with the Lagrangian method, because the way you would solve them is going to be exactly the same as with the Lagrangian approach, because you'll get the exact same equations, right? Anyway, we get this expression for T2 from the fourth equation, and now we will plug it into the third one. Notice that we have the m2 factor in every term, so we can just divide both sides by m2, and we can also multiply both sides by cosine theta 2 because we do not want anything in the denominator. Once we do that, we get the following equation. Now, take a look at this. Pairs of terms are of the same color, and those terms have the same non-trigonometric factors. For example, look at the blue-colored pair. They have both L1 and theta 1 dot squared, but they have different trigonometric factors. Take a look at the green terms here. They're my favorite because, thank God, they cancel out. We can also look at the purple terms. They both have L2 and theta 2 double dot, but different trigonometric factors. How can we use this to our advantage? Well, let's refresh our knowledge of some trigonometric identities. Here we have formulas for sine of the sum or the difference of two angles, for cosine of the sum or difference of two angles, and the fundamental trigonometric relation, sine squared plus cosine squared of the same angle is equal to 1. When we factor the same color terms and put them on the same side of the equal sign, thus leaving 0 on the other side, we see that for this purple term, we will get sine squared plus cosine squared of theta 2 in parentheses, which will leave us with only L2 theta 2 double dot. If we do the same thing for the blue terms, we will get sine theta 2 cosine theta 1 minus sine theta 1 cosine theta 2 in parentheses, which is equal to sine of theta 2 minus theta 1. So the other term we get is L1 theta 1 dot squared sine theta 2 minus theta 1, and we will get the cosine of the difference of these two angles for the red pair. The gravity is the same color as before because it doesn't have its pair. When we do all of this, we arrive at the following equation. And would you look at that? It is the same equation you get when you use the Euler-Lagrange equation for theta 2 in the Lagrangian method. It's incredible! Though it is not really all that shocking considering Newtonian and Lagrangian method are pretty much totally equivalent in the classical realm, so no one would expect that it is impossible to get this equation with both methods. Nevertheless, it feels so good to get the correct equation using Newtonian mechanics. But we still have one more equation to get, right? We now turn our attention to the first equation of motion. Now, before we go there, we're going to write down the expressions for both T2 sine theta 2 and T2 cosine theta 2 from third and the fourth equation. Why? Because the first equation contains T2 sine theta 2 and the second equation has T2 cosine theta 2. We don't want to plug in the T2 we expressed into both of the equations, the one we expressed before, because the math is just going to be so much more unbearable, so we'll do it in this way. Now, let's plug in T2 sine theta 2 into the first equation. From here, we can express T1, which will then plug in the second equation along with T2 cosine theta 2. Yeah, it looks pretty horrific, but we will make it less horrific by multiplying both sides by sine theta 1, so we don't have any denominators. Once again, you will notice that pairs of terms have the same non-trigonometric factors. Some of them thankfully cancel out, some of them connect to give us sines and cosines of difference of two theta angles, or sine squared plus cosine squared, etc. It is a simple exercise to do this step by step at home if you decide to engage in this problem yourself, but I'll just write down the final equation. And again, this is the same equation you get if you use Euler-Lagrange equations for theta 1 in the Lagrangian method. That is so incredible, and it really goes to show that these two formulations really yield the same result for same mechanical systems. We can now see these two equations together in their full glory. It's beautiful. It's hard to describe it with words only. Although it is really annoying to deal with a lot of simple but mind-numbingly boring math, God, it feels so incredibly satisfying to be able to derive the equations for a double pendulum without the Lagrangian and the Euler Lagrange equations. With the Lagrangian method, you basically don't think at all. It's really just math. But here you actually think about what's going on. What forces are causing this motion? What does it affect the system? You even get the expressions for tension forces if you want to study them later. And that's not the shit on Lagrangian mechanics. Oh no, 99 out of 100 times, if I have a complicated system, I'm going with the Lagrangian. It's a beautiful theory and it deals with these kinds of systems in astoundingly simple ways. But it is nevertheless a great exercise and a challenge for yourself to give Newton's laws a try. Not only is getting the right solution with Newton such a rewarding experience, but it will also put your knowledge and intuition about forces to the test, something we, especially as physics students, very rarely do once we learn about the other formulations of classical mechanics. But you do you, brother, right? So that's that. I hope you enjoyed this video, and I also hope you learned something new today. I haven't seen any other videos covering this, so I thought might as well, even though it is radically different from majority of the content I've been creating for years. But I figured I could put some of my physics knowledge to good use, finally. Therefore, you have this video. If you like this video, I might consider doing more videos like this in the future. I'll hopefully be able to buy some better recording equipment in the near future. And if you have any suggestions or questions about this video, we can talk it out in the comments. Also, consider liking the video if you liked it, maybe even subscribing to kind of motivate me to do shit like this if you enjoy it, whatever. But anyway, that's it for today. Bye-bye.